question that I'm quite frequently asked by upper sixth students is to revise the difference between a strong and a weak acid. Okay, now you can look at the chemical structure and make a good guess about a molecule, about whether it will be a strong or weak acid. All acids have something in common. They all contain hydrogen ions. That's actually strictly hydroxonium ions. More about that in a moment. Right, so if I take the classic example of a strong acid, hydrochloric acid, this is HCl in aqueous solution. Right, how is this molecule able to dissociate into hydrogen ions and chloride ions? Let's look at what's going on here. I've got very electronegative chlorine there. Chlorine is an electronegative element. It means it's greedy for electrons. So there's a covalent bond sat between the hydrogen and the chlorine atom, but electronegative chlorine is pulling that electron pair over towards the chlorine side. So it's sat over towards this right-hand side. If you can imagine that that chemical bond is a bit like a taut guitar string. It's under a lot of tension. Chlorine is tugging to come over this way, pulling the electron pair over to the right. And in the right environment, that guitar string or bond can go ping. It can just break. A suitable environment for that process to happen is to react this with water. If you put hydrogen chloride into water, if you take the gas and put it into water, it will dissociate into hydroxonium ions and chloride ions. These are the ions that make it an acid, the solution acid. The chloride ion is nothing to do with it. You think about when you're swimming around in the sea, you're surrounded by billions of chloride ions from the salt, and it doesn't have any effect at all. So this bond has gone snap in the presence of water to form hydroxonium ions and chloride ions. Okay, so this is a strong acid. Strong acid means that it's very, very good at doing that job. It's very good at coming right over to this side here. A-level students will know that all reactions in theory are reversible. You can think of them as able to go two ways, and you can think of it there as an equilibrium. Is the reaction more gone to one side or more remaining on that side? If I just put a double arrow in, this reaction has come right over to the right-hand side. It 99.9% has come over here. Okay, so it's mainly these ions here. That's what makes it a strong acid. It's a star striker at breaking up. Even when the acid is in dilute solution, it still is very good at doing that job. It's intrinsically good at dissociating into ions. So that's precisely what I mean by a strong acid. Another example is sulfuric acid. So I'd say to students, if you look at the structure of this, H2SO4, you look at that and you think, well, what is it about that structure that lends itself to being a strong acid? You've got 1, 2, 3, 4 electronegative oxygens. You remember, electronegative means it's greedy for electrons. It pulls electrons towards it. So if you think of the electrons being pulled this way and being pulled that way and being pulled that way, again, these bonds are under terrific strain. They're like those guitar strings again, a fantastic tension, ready to go ping. When those bonds break, the hydrogen atoms break off as hydrogen ions because of this environment. So what have these two molecules got in common? I've got this electronegative chlorine here, I've got electronegative oxygen here, stretching these bonds to the extent that they, in the right environment, in other words in water, you need water for this to happen, the bonds break and I get my hydroxonium ions. So the way that happens is that H2SO4 this time needs 2 water molecules because I've got 2 acidic hydrogens in that structure. And this comes over to 2 hydroxonium ions plus a sulfate ion. Okay, so in this case, I get 2 acidic hydroxonium ions, and this is called a diprotic acid. This is a monoprotic acid. Remember the approach a minute ago about having reversible reaction? If I think of it as reversible, the equilibrium is strongly over on the right-hand side like that. It's over there. This is a star striker of an acid. Just a little bit of water, it falls apart. So there are many other strong acids. Nitric acid is another example. And again, if you just look at the structure, you can see the electronegative oxygens cause the dissociation. I now want to contrast this with a weak acid. Now you'll all be familiar probably with vinegar, which is ethanoic acid, sometimes called acetic acid. This is what we put on our fish and chips in a dilute solution. And this is a weak acid, and let's look at why that is a weak acid. We can discern that from looking at the structure. So here's a couple of strong acids. Again, this one was a strong acid. Okay, moving on to a very good example of a weak acid. This molecule here is ethanoic acid, 2 carbons, therefore F, ethanoic acid, more commonly known as acetic acid, or more commonly known to the layman as vinegar when it's in dilute solution with other things added to it. Okay, so this is a weak acid, and I'm going to explain why. Just a little footnote here for you. If you get a wasp sting, wasp stings are alkaline. And so if you do unfortunately get a wasp sting, you should put a little bit of vinegar on it to neutralize it. Okay, actually bee stings the other way around, you need to find an alkali to add to it, so that might be more difficult. Anyway, getting back to this here, if you look at the structure of this, you can probably identify which is the hydrogen that is going to break off. We've got options here, we've got those 3 hydrogens there and this one here. This is the acidic hydrogen that will break off as an ion. Okay, so again, I'm looking at how much stress is that bond under? How electronegative is this electron pair here, what it's joined to here? Immediately you'll say you've got 2 electronegative oxygens there, which is rather sort of belies the truth of this molecule here, because yes, you've got oxygen pulling electrons that way, pulling electrons towards it, so it's trying to break the bond. But over here, this CH3 group is a methyl group, and a methyl group has a positive inductive effect. A positive inductive effect. Right, now in plain language, this is kind of the reverse to electronegativity. It actually pushes electrons away from itself. The reason why this pushes electrons away, because hydrogen atoms tend to be electron releasing. They've only got 1 proton. These 3 hydrogens only got 1 proton, and they tend to let electrons move away. So if you can see this process happening, you've got electrons shifting more down this end of the molecule. What effect is that going to have on the stress in that bond? We've got the oxygens ripping the bond or trying to break the bond apart. I've got these 3 hydrogens pushing electrons towards that bond. In other words, they're reinforcing the bond and kind of making it stronger, therefore less likely to break. So my guitar string is less likely to snap with the presence of a methyl group. A methyl group has this positive inductive effect. Hydrogen joined to carbon tends to shift electrons that way. However, we still get an acidic effect. So the equation for this, I won't draw the displayed structure like that. So here's my ethanoic acid molecule. That reacts with water. That's liquid. Okay, that's called ethanoate ions. And that's hydroxonium ions as before. Any acid is only an acid when it has this ion. It could be lemon juice, it could be carboxylic acid, it could be nitric acid, whatever it is, it will be the hydroxonium ions that cause the acidic effect. Okay, now let me just talk about the equilibrium aspect of this. If I think of that as a reversible reaction, which it's moved a bit this way or moved a bit that way, or not moved at all, that's what I'm saying. The truth about this reaction is that the equilibrium is significantly over on the left-hand side. In this case, it hasn't budged that much over here. It's a bit sluggish. It's a bit of a third division player as an acid. It doesn't really want to play this game because of the positive inductive effect of the methyl group shoving electrons towards that bond, reinforcing that bond and making it stronger and less likely to ping, break. Okay, so what it means is that instead of it being nearly 100% dissociated, it's only slightly dissociated. Okay, so this reaction's only comes slightly this way. There is only a small amount of hydroxonium ions. Okay, so that's why we can drink vinegar, as long as it's not too concentrated, and it's not particularly hazardous. It is intrinsically not good at dissociating into these ions. It intrinsically is not good at doing that. If you ask me the question, is concentrated ethanoic acid dangerous when it's very, very concentrated? The answer is yes. Because when it's concentrated, even though it's not a star player at breaking up, there's going to be a lot of these and it could be hazardous. But nowhere near as hazardous as your concentrated hydrochloric or your concentrated sulfuric. Okay, so don't think it's always safe, because it isn't. Okay, so there's my weak acid, and the position of equilibrium lies predominantly on the reactant side, with only a little bit of dissociation into ions over here. Okay, I want to develop that now and look at another molecule which is similar to this and decide which one is stronger or weaker. Okay, let's develop the discussion a little further. Ethanoic acid, we've just been talking about, is part of a family of acids which are called carboxylic acids. A carboxylic acid has this group here, COOH. All carboxylic acids have that little functional group there. Right, it's a whole family of acids in organic chemistry, and that's the most well-known one. There is this example here, propanoic acid, prop because of 3 carbons. And I've also got another one to compare, which is methanoic acid because of 1 carbon. By the way, methanoic acid traditionally was known as formic acid, and that's the acid that ants spray, some species of ants spray as a defense mechanism. The Latin name for ants is formica, and it's also used as embalming fluid. Anyway, that's a digression. The question I want to ask immediately is, which do we think is the stronger acid? Ethanoic acid or propanoic acid? One of them is stronger than the other. You remember the point about an acid reaction is that this OH bond needs to snap, it needs to go ping, and then hydrogen can break away as a hydrogen ion. So we need to look at the environment, the molecular environment of this OH bond. That gives us clues. The 2 oxygens is common in both structures, but this time I've got an ethyl group here, an ethyl group which is C2H5 compared with a CH3 group. You recall a couple of minutes ago we were talking about the positive inductive effect, that hydrogens tend to have a push of electrons towards this end of the molecule. Well, if we look at this example here, I've now got 5 electrons in the ethyl group. This is the ethyl group, all pushing electrons down towards the right-hand side. This bond is under stress because of electronegative oxygen around it, but it's also having a counter effect from the 5 hydrogens, which are pushing the other way. They're reinforcing that bond and making it stronger. So the immediate question is, which will be the stronger bond in propanoic or in ethanoic? And if you think about that for a second, the answer means that the bond will be stronger in the propanoic acid because more electrons are being pushed down, reinforcing that bond. So the question is, which of the 2 acids is the stronger or weaker? The stronger acid is ethanoic acid because this bond breaks more easily. This one has a more reinforced bond and doesn't break so easily. Okay, so propanoic acid is a weaker acid than ethanoic acid. Okay, I could write the dissociation equation. It'd just be very similar to the example for ethanoic. The equilibrium would be further to the left. It doesn't want to break up. It's a fourth division player now. It really struggles to break up. A strong acid dissociates completely or virtually completely. A weak acid dissociates, breaks up only partially. Okay? Right, let's look at one more contrasting example. I've got methanoic acid here, okay, with one carbon there. And the question is that OH bond. Remember, the end game is that OH has to snap off and form hydrogen ions. It needs to come off and form H+. This time I've only got one hydrogen compared with 5 there and 3 there. So that little hydrogen by itself can't do much to strengthen that OH bond. So therefore, in terms of acid strength, this will be the stronger of the 3 because there's not much positive inductive effect from that hydrogen. There's a weak inductive effect from that hydrogen there. So okay, so that bond is not as reinforced as previously, and so this is the strongest of the 3. Okay, so putting them in order, methanoic is stronger than ethanoic, which is stronger than propanoic acid strength. So if I give you other examples with different numbers of carbons and hydrogens, you should be able to predict quite rationally, the more carbons and hydrogens I've got down there, that's going to make the acid weaker because it strengthens the OH bond. Okay, none of this discussion happened with hydrochloric acid, where you had very willing partners in that previous discussion. HCl, very electronegative chlorine. Hydrogen is, it's only one hydrogen there, it can't do very much. And so that snaps very easily, and that's why it's a strong acid. Okay, carboxylic acids are intrinsically weak acids, even when they're concentrated. It's just intrinsically not good at dissociating. Okay, thank you.